Let's use vectors in practical applications. So, vector examples. My favorite type of example would be an airplane example. Here's the scenario. We have a Cessna 150. It's a two-seat airplane, so it doesn't go very fast. It goes 110 miles per hour. And let's say it is pointed in the direction of 40 degrees east of north. So if you've ever read a compass rose, then you would just say 40 degrees. Now we have wind that is blowing. So wind is blowing. Let's say it's blowing 20 miles an hour from the south. So that is basically meaning to the north. Wind is always discussed as from. So if we set these up as vectors, now let me draw this out, and I'm going to take it outside of the navigation world back into the math world for a minute when we get done. But if I've got my Cessna and it's going 110 miles an hour, that's going to be the length or the magnitude of my vector. And I want it 40 degrees east of north. So it's going to be right along here. And that's going to be like that. So this is going to be 110 miles long, okay? And I've got a 50-degree angle here and a 40 here. Now, I need to add wind, which I've got this graph set up badly, but I've got to add a 20-mile-an-hour wind from the south. So it's right there. So here's the wind. And if I deal with this, I've got a combination. I've got to add them together, okay? So let's deal with the plane. Now let's take it out of navigation and into mathematics. As here, mathematics, we've got the x-coordinate, the y-coordinate, and so forth. So I'm going to go ahead and do that. I'm going to say that this plane has a magnitude of 110, and the vector for the direction that it has. In the x direction, if we talk about x, we commonly talk about cosine. So let's say cosine, and the angle from the positive x-axis is 50 degrees. The sine is the y part, so sine of 50. So our plane is the vector 110 cosine 50, 110 sine 50. I just did a scalar multiple of my direction angle. Now, the wind. We've got the wind. The wind, now using mathematics, so this is going to be minus 90, but that's where it's coming from. It's actually going 90. So our magnitude is 20. We'll have cosine of 90, sine of 90. Now that one's pretty easy to calculate actually. Okay, so that's equal to 20 and 20 cosine of 90, 20 sine of 90. All right, so let's take these two and add them together, because when you're up in the sky, the wind does determine a lot about the plane. So let's combine our forces. So let's take the plane vector plus the wind vector. So that the result is 110 cosine of 50 plus 20 times cosine of 90, which is actually plus 0, okay? And it makes sense, very likely, that a straight wind from the south would not move you left and right at all, so it's not going to alter the x part. Then we've got the y or the j component, which is 110 sine of 50 plus 20 times the sine of 90. Well, that is literally plus 20. So it's going to make all the difference in the world that direction. okay? All right, so let me get some numbers here off of the calculator so that we can figure some things out. So I'm going to put the calculator up here, and we're going to put them in. So if I do this, I've got 110 times the cosine of 50. Cosine of 50, and I've got my calculator in degrees. So that is, and I'm going to be approximate here, 70.7. Okay, so this is approximate, 70.7. And I'm going to take 110 times the sine of 50, close that, and add 20. So that one's 104.3. So 104.3. Now, how fast is the plane going? Well, let's find the magnitude. So the speed of the plane, and this is not of the plane itself, this is called ground speed because it's in relationship to the ground. So we're going to call that ground speed, is equal to the square root of this 70.7 squared plus the 104.3 squared. So let me get these and take the better values that I've got. So I'm going to take this one and square it. So square that, and then I'm going to add this one squared. So I've got this. Then I need the square root. So I raise it to the 1/2 power, just so I don't have to do much work. And I end up with approximately 125.9 or actually 126 miles an hour, right? Okay, so about 126 miles an hour. Now what's the direction? We need to know the direction. The direction, here is the y part and here's the x part. Why don't we take the tangent of theta is equal to the y over the x, or the j part, that's actually the j part over the I part, okay? So I'm going to literally do this all at once. I'm going to say theta is equal to the arctan, and then I'm going to put these numbers, okay? These. So 104.3 over 70.7, and I could take the more exact ones. So let me do that. I've got to take inverse tangent, so right there. And I want the 104, so I'm going to go up here and grab it. And then I'm going to divide by the 70.7. That one's a little more exact. And close parentheses, and I've got this angle. I've got theta is approximately 55.8570667, etc. Now, that's from the east, or from the positive x-axis. So if I wanted to talk about that in navigation, I would notice that, yes, in fact, we are in the first quadrant, but we're going 55.85 degrees up from horizontal. So here's horizontal, it's going this way. If I subtract that from 90, it's going to give me the bearing. So if I subtract it from 90, I am going to multiply it by -1, and then I'm going to add 90. That's going to subtract it from 90. So the bearing is approximately 34 degrees. So that means that the plane is not going the 40 degrees that it started, it's going about 34. Now, if the pilot's not careful, he or she will get lost in that. So they've got to pay attention. Okay, there's an example of vectors and flight.